Well, hello. Welcome to another video. In this one, I'm going to describe how you draw ray diagrams to locate and describe images in different lenses. So I'm going to actually try to get everything into one video here. So it's going to be a little lengthy, but I'm going to go a little faster than I did for the mirrors because this is not the first time you're seeing something like this. This is very similar to what we did with the images formed by mirrors. We just have to kind of alter a few of the ways that the rays are drawn. The math is pretty much identical, which is amazing. So I'm not really going to spend much time on the math. But if you need anything more than what this video offers, of course, you just need to find me live if I'm your teacher. I'm going to be referring to this page that you have that goes along with your packet. Down here are lenses, right below where we did things for mirrors. And I tried to write them in such a way that they're pretty succinct, but they're somewhat similar to what we did for mirrors. So I have, on the first example that you have, I have actually drawn one out for you. So this will give you something to refer to, but I'm going to do the second one kind of live here. And I'll refer to each of the rules as we go along. Again, so by the time you've done this one with me, and look back at number one, you should be able to see enough examples. Hopefully you can do the others on your own. I'm going to get a start on number 3 here, and then also I'll do one of the ones for the what we call a diverging or a double concave lens. So again, going to try to wrap a lot into this. If you need to just advance to whatever part you need, of course, that's the beauty of having this on video. So okay, so what we're looking at here is how light rays will go through a lens and refract. Actually, it will refract twice, once on the way in, once on the way out. But to simplify things, what we generally do in these ray diagrams is we treat the bending as though it all happens at one time, right in the middle of the lens. So a little artificial, but it works well. And we call the middle of the lens the principal plane. So you'll see it labeled here PP. And that is in addition to the principal axis, which we used for mirrors as well. That kind of goes right perpendicular to that, and it's got the focal points on it. So the focal points for lenses, very similar to mirrors, except that the light is going through the lens because it's made out of something like glass. And so the focal point will be on the other side is what the object is on. So we call that the focal point. And for this double convex lens here, or a converging lens, this will be the focal point. But because lenses kind of work both directions, they're not like mirrors where only one side reflects, we have a focal point over here. So the one that's on this side, the same side as the object, that's what I will refer to in the ray diagram rules as the other focal point. So you'll see here in rule number 2, it says the other focal point. And again, all of this is kind of described up here in the figure as well. If you need to refer back to that, that might be helpful. So I'm just going to start drawing some rays here to get this moving along. And again, you'll find some very similar rules to what we did for mirrors. So here's a ray that's coming in parallel to the principal axis. And the light will bend a little bit downward on the way in and a little bit more downward on the way out. But we will treat the bending as though it happens right here at the middle at the principal plane. And that is the ray that will refract directly through the focal point on the other side of the lens. And then the ray that goes through this focal point, the other focal point, the one on the near side, I guess we'll call it, that's the one that when it hits the lens, it will bend and refract parallel to the principal axis. So again, very, almost kind of like reverse of rule 1. And then, honestly, the easiest ray to draw, I'm going to do this in green, is rule number 3. If it hits right at the center of the lens, I say at the intersection of the principal plane and principal axis, that is the one that will not refract basically at all. It actually refracts a little on the way into the lens and a little on the way out, but we treat it as though it goes straight through. And then, like we did before, we're looking for what our eye sees. So our eye now is over on this side. So here's one person's eye, here's another person's eye, might have a person up here, person up here looking, and we all see the same image along different lines of sight. But we're looking for, where do all of these rays seem to be coming from? Well, they seem to be coming from right here. So that's where our eye will see the image of this arrowhead. And again, like mirrors, the rest of the arrow is just between there and the principal axis. So in this case, because these rays are really intersecting, and you'll see in a lab that we do in the classroom that we can put this image on a card, on a piece of paper, that is a very real image. Okay, so real image there. In this case, it's a little bit taller than the actual object. The object was 3. This is closer to 4. On this example up here, where the object was pretty far away, it made the image a little bit smaller. Okay, so that's how you do the rays. Again, I am not going to show the math here because the math is almost identical. You have to count, and when you count like what your focal length is, you start from the center of the lens where this principal plane is. So 1, 2, 3, 4, 5 would be the number for our focal length here. And then 6, 7, 8, 9. 9 would be the object distance. So you're going to put that into the mirror/lens equation. And again, in the form that I use, that's just the easiest. You put the inverse of the focal length, that was 5, minus the inverse of the object distance, which was 9. And then you invert the difference between those, and that will give you your image distance. Okay, yeah, I'm not going to do the math because we've seen that already. Okay, so what happens, and you remember this from the concave mirrors, funny things happen when you get really close. So let me show you here. Rule 1, very similar. Starts out parallel to the principal axis. It will refract rather, I almost said reflect like it's a mirror. Refract through the focal point, like that. And then the one that goes through this other focal point on the way to the lens is the one that comes out parallel. Well, obviously it can't be going through this because it would be going the wrong direction. But it can come from a direction that seems to be from this other focal point. So I'm going to line up this focal point here, the tip of the arrow, and I'm just going to draw the ray coming from the arrowhead, but it's coming from the same direction that something would have come from this other focal point. So that's our incident ray. And then the refraction happens right here, or at least we draw it that way. Remember, we're drawing things a little simply. And again, I know some of you, when you did mirrors, didn't draw the actual ray. I want to see the actual refracted ray, and then you can draw the extension. See, what happens now is, oh, let me draw this last one. Again, this is the easiest one to draw, so we might as well draw it each time. The one that goes right through the center of the lens is the one that effectively doesn't bend at all. 2 tiny little bends just amounts to almost nothing. So here's an eye looking along that green ray. Here's an eye looking along the red ray. And another eye. And of course there could be all kinds of other eyes looking at this lens. So what they see is all of the same image. Where do these rays seem to diverge from? Back here somewhere. So we extend these with dashed lines. This is in the directions, by the way, to use dashed extensions of your refracted rays. Again, another common mistake is to extend the incident ray. That's not going to get it for you. You extend what the eye is seeing, which are these refractions, and right back there is where this image seems to be. Now, I say seems to be because this is an illusion. The real rays are out here, but they seem to be coming or diverging from this location back on the same side of the lens as where the object is. So we call this one a virtual image. That's why I drew it dashed, virtual image. And when you do the math, your virtual image means the image distance will come out negative. Okay. So if you don't get a negative, that means you did something wrong. All right. And then the last one I want to do is one of these diverging or double concave lenses. So again, I've drawn an example here for you, but let me do one quickly live. And when you're using these rules, the parts in parentheses are going to have to be added for the double concave lenses. So here's the the difference, the biggest difference is these lenses tend to, when light hits them, they tend to diverge the light away from the other rays. Okay, kind of spread it out. And so, I'll show you what this means. So this first ray, I've been drawing it in red, so I'll stick with that. If it comes in parallel to the principal axis, and it hits the lens, again, it refracts a little bit on each side of the lens, but we're drawing it. And the way this reads is, parallel to the principal axis will refract as though they come through the focal point. So here's what's really different. The focal point on this kind of a lens is a virtual focal point, and it is on this side, the virtual side. Okay, so that's described up here, the focal point. It's a virtual focal point, if you want to call it that. So you have to put your ruler, now don't draw the light actually back here. You're drawing the real light up here where the real stuff is, going through the lens. And then you'll see in a moment we're going to have to extend that. But rule number 2, incident rays that would go through the other focal point will refract parallel. So again, this is a case of putting your ruler down first, but you're not going to draw all the way along. So if it would go through this focal point, now this is not the real focal point for this lens because this is not a converging or double convex lens. It's a diverging lens. So this is the other, as I'm calling it. This is somewhat my language, but it works pretty well. So when it gets to the center of this is when it refracts parallel to the principal axis. Like that. And then, oh, I love this rule because this rule is identical for both lenses. If it goes through the thin center of the lens, there will be such minor refraction that you can just draw it as though it goes straight through. So what do these 3 eyeballs all recognize? They see this image directly back along their line of sight. So I'm going to extend these lines of sight. Now remember, this red one was the one that I originally drew as though it was coming from this virtual focal point. So I'm going to extend that back. The blue one came out parallel, so that person's eye, the blue eye, will see it as though it's coming from back here. And here's the great thing about the green ray. It is its own extension. It's just a single line. So here is that spot. Again, I've got a tiny little one drawn up here, but this one's a little bit easier to see. Now, it's tough because I want you to draw these dashed. When they're virtual like this, there's the arrowhead, and then we got this tiny little stem of the arrow right there. So, hard to see. But right there, in fact, sometimes I just do this. This is the image. It is a virtual image. When you get a virtual image, no matter what kind of mirror lens you have, you will get a negative image distance, and it will always be upright. As long as you've only gone through one mirror or one lens, it will always, every virtual image will always be upright. That's one way of knowing that it's virtual. Your brain really doesn't know the difference between real and virtual, so that's one way of kind of indicating that to your brain. So, again, the math here, pretty much the same, except negative focal length. That's what you have to remember on these diverging lenses for the double concave lenses. And if you'll remember that, the math works out perfectly, just like it does with all the other mirrors and lenses. It's pretty amazing that this one equation here, I call it the mirror/lens equation, and then the magnification equation is still the same. Those are so versatile that they will work with both kinds of mirrors and both kinds of lenses. Pretty great. So, okay, that's as much as I'm going to do. I'm running over 14 minutes here, and that's long enough. So, hopefully you got what you needed from this. Again, get some live help from me, or there's plenty of other resources that you can use to supplement this. Hope it was helpful. Thanks for watching.